Hello there, and welcome to the Sleepy Library. Tonight, we are embarking on a gentle journey through the profound and inspiring story of space travel, where humanity has reached beyond the cradle of Earth to touch the cosmos itself. This is not simply a recitation of dates and distances. It is a journey through wonder, courage, and the quiet determination that has carried us from the first tentative steps into orbit to footprints on the moon and rovers exploring distant worlds. Out there, in the silent expanse, are spacecraft still traveling, messages carried on golden records, and the echoes of voices that first spoke from beyond our atmosphere. These are not just machines and missions. They are extensions of human curiosity, testaments to what we can achieve when we dare to reach for the stars. If you enjoy these peaceful explorations of science and discovery, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the concerns of your day drift away like debris floating in the weightless void. Allow your mind to settle into the rhythm of this story, as steady and patient as an orbit around Earth. Let's begin. The first human to journey into space spent just 108 minutes beyond Earth's atmosphere. On April 12, 1961, Soviet cosmonaut Yuri Gagarin climbed into the Vostok 1 capsule, a small metal sphere barely large enough to hold a single person. At 9 hours and 7 minutes Moscow time, the rocket ignited beneath him, and he lifted away from the planet's surface for the first time in human history. The flight was brief, a single orbit around Earth that took less than 2 hours from launch to landing. Yet, in those 108 minutes, everything changed. Gagarin looked down at Earth through a small porthole and saw the blue curve of the planet against the blackness of space. He saw clouds swirling over oceans, the thin line of the atmosphere glowing softly at the horizon. He radioed back to ground control with a simple phrase that would echo through history, describing Earth as beautiful. When his capsule returned, parachuting down into a field in the Soviet Union, Gagarin emerged as the first person to have seen our world from outside. The first to know what it feels like to leave the ground and not come back down for more than an hour. His flight proved that humans could survive in space, that we could venture beyond the atmosphere and return safely. It opened a door that would never close again. Space travel did not begin with a single leap. It began with years of careful preparation, with unmanned rockets carrying instruments and animals into the upper atmosphere and beyond. Before any human sat atop a rocket, dogs and chimpanzees rode in their place, test subjects whose journeys revealed the challenges of leaving Earth. These early missions tested life support systems, studied the effects of weightlessness, and proved that living creatures could survive the journey. Each flight added to our understanding. Each success built confidence. Each setback taught valuable lessons. By the time Gagarin climbed into Vostok 1, engineers had already sent spacecraft beyond the atmosphere dozens of times. They had learned how to build capsules that could withstand the heat of re-entry, how to create environments where a living being could breathe and survive in the vacuum beyond. They had mapped the invisible forces that would act on a body in orbit, the peculiar sensation of weightlessness, the way blood pools differently when there is no up or down. All of this knowledge, gathered patiently over years of testing and refinement, culminated in that single orbit, that first human journey beyond the sky. The United States followed less than a month later with Alan Shepard's flight. On May 5, 1961, Shepard rode the Mercury capsule Freedom 7 on a suborbital arc that carried him to an altitude of 116 miles before falling back to Earth. Unlike Gagarin's orbital flight, Shepard did not circle the planet. His trajectory was a high parabolic curve, 15 minutes of weightlessness and wonder before splashing down in the Atlantic Ocean. But those 15 minutes mattered. They proved that American technology could also carry a human beyond the atmosphere. They showed that the United States could join this new frontier. Shepard's calm demeanor during the flight, his steady voice on the radio as he described what he saw, reassured a nation that space travel was not just possible, but could be done with confidence and control. His capsule was recovered by helicopter, lifted from the waves and brought to a waiting aircraft carrier, where Shepard emerged smiling, ready to tell the world what it felt like to touch the edge of space. The early years of human spaceflight were marked by competition, a race between two superpowers to demonstrate technological prowess and national will. The Soviet Union and the United States each sought to be first, to achieve milestones that would prove their systems superior. This competition drove rapid advancement. Within months of Gagarin's flight, both nations were launching more cosmonauts and astronauts, extending the duration of missions, testing new capabilities. German Titov became the second Soviet in space, spending more than a full day in orbit. John Glenn became the first American to orbit Earth, circling the planet 3 times in February 1962, while millions watched and listened. Each flight pushed the boundaries a little further. Each mission tested something new. They learned how to eat in weightlessness, how to sleep when orbiting Earth every 90 minutes, how to work and think and function in an environment that defied every instinct honed by evolution on solid ground. They discovered that the human body adapts, that balance and orientation shift but do not disappear, that with training and preparation, people can thrive even when floating free. The spacecraft of those early years were small and cramped. The Mercury capsule that carried American astronauts could barely fit a single person lying on their back. There was no room to move, no way to stand or stretch. The cosmonaut in a Vostok capsule had slightly more space, but still sat in a seat designed to hold them firmly during the forces of launch and re-entry. These were not vessels for exploration in the traditional sense. They were survival pods, engineered to keep a human alive long enough to prove it could be done. The controls were minimal, much of the flight managed from the ground by teams of engineers watching telemetry and sending commands. The astronaut or cosmonaut was as much a passenger as a pilot, present to observe, to report, to experience what no one had experienced before. Their courage lay not in controlling the craft, but in trusting the systems, in riding the rocket into the unknown with nothing but faith in the engineers who had designed it, and the procedures that had been tested again and again. And when they returned, when the capsules splashed down or parachuted to Earth, they brought back something irreplaceable: the knowledge that humans could go there and come home. The Gemini program followed Mercury, expanding what American astronauts could do in space. Launched between 1964 and 1966, the Gemini missions carried 2 astronauts at a time, giving them more room to work and experiment. These flights tested techniques that would be essential for the Apollo moon missions. Astronauts practiced rendezvous, flying their spacecraft close to another object in orbit and matching speeds with precision. They learned how to dock, how to connect 2 spacecraft while traveling at thousands of miles per hour. They went outside their capsules, performing the first American spacewalks, floating in the void while tethered to their craft. These extravehicular activities, as they were formally called, revealed both the possibilities and challenges of working in space. The first astronauts to venture outside struggled with the stiffness of their suits, with fogged visors and exhaustion from simple movements. But they learned. They developed techniques, designed better handholds, trained underwater to simulate the sensation of weightlessness. By the end of the Gemini program, astronauts could spend hours outside their spacecraft, moving with confidence and completing tasks that had seemed impossible just months before. The longest Gemini mission lasted nearly 14 days, 2 weeks in orbit that tested the limits of human endurance in weightlessness. Astronauts Frank Borman and Jim Lovell circled Earth for almost 200 orbits, long enough to experience the full range of adaptation that comes with extended spaceflight. They grew accustomed to floating, to the way objects drifted when released, peculiar sensation of sleeping while strapped to a wall. They learned that the body changes in subtle ways when freed from gravity's constant pull, that blood redistributes, that muscles and bones begin to weaken without the resistance they evolved to handle. These lessons would shape how future missions were designed, how exercise and nutrition were managed, how astronauts prepared for the longer journeys that were coming. The Gemini program was a bridge, a stepping stone between the brief first flights and the ambitious goal that President Kennedy had set for the nation, to land a man on the moon and return him safely to Earth before the decade ended. The Apollo program represented the culmination of all that had been learned. It was an endeavor of staggering complexity, involving hundreds of thousands of people working toward a single goal. The spacecraft itself was unlike anything that had come before. It consisted of 3 parts: the command module, where the crew lived and worked, the service module that provided power and propulsion, and the lunar module, designed to land 2 astronauts on the moon while the third remained in orbit. Each component had to function perfectly, had to survive the journey to the moon, perform its role in the intricate dance of lunar orbit and landing, and then bring everyone home. The rocket that would carry this spacecraft, the Saturn V, was the most powerful machine ever built. A towering structure taller than a 30-story building, capable of lifting over 100 tons beyond Earth's gravity. When it launched, the ground shook for miles around, the roar loud enough to rattle windows and deafen anyone too close. It burned thousands of tons of fuel in the first few minutes of flight, propelling the astronauts through the atmosphere and into space with a force that pressed them back into their seats. The road to the moon was not without tragedy. On January 27, 1967, during a routine test on the launch pad, a fire broke out inside the Apollo 1 command module. The cabin was filled with pure oxygen, which made the fire spread with terrifying speed. Astronauts Gus Grissom, Ed White, and Roger Chaffee were trapped inside, unable to open the hatch quickly enough. All 3 lost their lives in a matter of minutes. The fire was a devastating blow to the program and to the nation. It forced a complete re-evaluation of the spacecraft's design, led to changes in materials, procedures, and safety protocols. NASA delayed flights for more than a year while engineers redesigned the hatch, switched to a mixed atmosphere during ground tests, and eliminated flammable materials wherever possible. The tragedy was a reminder that space travel carried real risks, that the technology was still being perfected, that even the best-laid plans could fail in ways no one anticipated. But it also strengthened the program. The changes made in response to Apollo 1 saved lives in later missions. Astronauts who flew after understood the risks they were taking and chose to continue anyway, honoring the memory of Grissom, White, and Chaffee by carrying the miss. Apollo 8 was the first mission to carry humans beyond Earth orbit. Launched in December 1968, it was a bold and somewhat impromptu decision to send astronauts all the way to the moon, even though the lunar module was not yet ready for flight. The mission's goal was to orbit the moon, to prove that the command and service modules could make the journey, navigate into lunar orbit, and return home safely. Astronauts Frank Borman, Jim Lovell, and Bill Anders spent 3 days traveling outward from Earth, watching as their home planet grew smaller behind them. They became the first humans to see the far side of the Moon, the hemisphere that never faces Earth, a landscape of ancient craters and maria unseen by human eyes until that moment. On Christmas Eve, as they orbited 60 miles above the lunar surface, they broadcast a live television message to Earth. They read from the book of Genesis, describing creation while the moon passed below them in stark black and white. Then Anders turned his camera toward the horizon and captured one of the most iconic images in history, Earthrise, the blue and white planet rising above the grey desolation of the moon. That photograph changed how people saw their world, a fragile oasis of life suspended in the void, the only home we have ever known. The Apollo 11 mission achieved what Kennedy had promised. On July 16, 1969, Neil Armstrong, Buzz Aldrin, and Michael Collins launched from Cape Canaveral, beginning the journey that would place the first humans on the surface of another world. 4 days later, Armstrong and Aldrin descended in the lunar module Eagle, while Collins remained in orbit aboard the command module Columbia. The landing was tense, the computer guiding them toward a crater field littered with boulders, forcing Armstrong to take manual control and fly beyond the planned landing site. Fuel ran low, alarms sounded, but Armstrong kept his calm, steering the fragile spacecraft to a flat patch of ground in the Sea of Tranquility. When the landing pads touched down, Armstrong radioed back to Earth with the words, "The Eagle has landed." Hours later, after checking systems and preparing their suits, Armstrong opened the hatch and climbed down the ladder. He paused on the last rung, then stepped off onto the lunar surface, speaking words that would be remembered forever. That's one small step for man, one giant leap for mankind. Aldrin joined him, and together they spent just over 2 hours walking on the moon, collecting rocks, setting up experiments, planting the American flag. They moved with a strange hopping gait, adapted to the moon's gravity that pulled them with only 1/6 the force of Earth. Everything they did was slow, deliberate, conscious of the fact that they were the first, that every step was history being made. 5 more Apollo missions successfully landed on the moon between 1969 and 1972. Each built on the lessons of the last, venturing farther from the landing site, spending more time on the surface, conducting more detailed scientific investigations. Apollo 12 landed with pinpoint accuracy near an old robotic probe, proving that astronauts could target specific locations on the lunar surface. Apollo 14 carried the oldest astronaut, Alan Shepard, who had been the first American in space nearly 10 years earlier. He hit golf balls on the moon, watching them arc silently through the airless sky. Apollo 15, 16, and 17 brought the lunar rover, a battery-powered vehicle that allowed astronauts to travel miles from their landing site, exploring valleys and mountains, drilling deep into the lunar soil, collecting samples from geological features that told the story of the moon's formation and history. The last mission, Apollo 17 in December 1972, carried geologist Harrison Schmitt, the only scientist to walk on the moon. He and Eugene Cernan spent more than 22 hours outside the lunar module over 3 excursions, gathering the most extensive collection of samples ever returned from another world. The Apollo program ended not because the technology failed, but because priorities shifted. The cost of sending humans to the moon was enormous, and after 6 successful landings, public and political support waned. 3 more missions that had been planned were cancelled. The rockets and spacecraft intended for them were repurposed or placed in museums. The last astronauts to walk on the moon left tire tracks and footprints that remain undisturbed to this day, preserved in the airless environment, waiting for the next generation to return. Apollo 17 commander Eugene Cernan was the last human to set foot on the lunar surface before climbing back into the lunar module for the final time. His last words from the moon were a promise that we would return, that humanity would not abandon this place, that future explorers would follow the path that he and 11 others had walked. More than 50 years later, that return is being planned. New missions designed to bring astronauts back to the moon, to establish a more permanent presence, to use the moon as a stepping stone for journeys deeper into the solar system. The transition from exploration to habitation began with Skylab, America's first space station. Launched in May 1973, Skylab was a large orbital laboratory created from the third stage of a Saturn V rocket. It provided far more room than any previous spacecraft, with a workshop, sleeping quarters, and a solar observatory. 3 crews visited Skylab over the course of a year, staying for periods ranging from 28 to 84 days. They conducted experiments in medicine, astronomy, and materials science, learning how the human body adapted to long-duration spaceflight, how plants grew in weightlessness, how metals behaved when melted without gravity to pull them into a specific shape. The longest mission, Skylab 4, set a record that would stand for years. Astronauts spent nearly 3 months in orbit, long enough to experience the full cycle of adaptation, the initial disorientation, the gradual acclimation, the subtle physiological changes that come with extended time in microgravity. When they returned, they needed help walking, their legs weak from months without bearing weight. But they recovered quickly, and the data they brought back helped shape how future long-duration missions would be designed. Skylab also demonstrated the importance of repair and maintenance in space. The station's launch damaged one of its solar panels and a thermal shield, threatening the entire mission before it even began. The first crew to arrive spent days performing emergency repairs, deploying a makeshift sunshade to keep the station from overheating, freeing the jammed solar panel to provide enough power. Their work saved Skylab and showed that astronauts could fix problems in orbit, that human ingenuity and adaptability were essential for sustaining life in space. The station remained in orbit until 1979, when increasing atmospheric drag finally pulled it down. It disintegrated over the Indian Ocean and Western Australia, scattering debris across the outback. By then, NASA was already planning its next major program, the Space Shuttle, a reusable spacecraft that would change how humans accessed space. The Space Shuttle represented a new philosophy in space travel. Instead of capsules that splashed down in the ocean and could be used only once, the shuttle was designed to launch like a rocket, operate in orbit like a spacecraft, and land like an aeroplane. It could carry larger crews, up to 7 people at a time, and had a cargo bay capable of deploying satellites, carrying modules for space stations, and even retrieving damaged spacecraft for repair. The first shuttle, Columbia, launched on April 12, 1981, exactly 20 years after Gagarin's flight. Astronauts John Young and Robert Crippen rode it into orbit, tested its systems, and brought it home to a runway landing in the California desert. It was the first time a spacecraft designed for space had landed on wheels instead of parachutes or splashing into water. The shuttle program would go on to fly 135 missions over 3 decades, carrying astronauts, satellites, scientific instruments, and modules for the International Space Station. It became a symbol of routine access to space, though routine was perhaps the wrong word for something so complex and dangerous. The shuttle's design included risks that were not fully appreciated until tragedy struck. On January 28, 1986, the Shuttle Challenger broke apart. 73 seconds after launch, resulted in the loss of all 7 crew members. The disaster was caused by a failed seal in one of the solid rocket boosters, a flaw that had been identified but not adequately addressed. The explosion was witnessed by millions, including schoolchildren who were watching because teacher Krista McAuliffe was aboard, selected to be the first private citizen to fly in space. The loss was devastating, a stark reminder that space travel remained inherently dangerous, that every launch carried risk, no matter how many times it had been done before. NASA grounded the shuttle fleet for more than 2 years, redesigning the boosters, improving safety protocols, and reinforcing the understanding that spaceflight demanded constant vigilance. When the shuttles returned to flight in 1988, they did so with renewed caution and a deeper respect for the challenge. 17 years later, another shuttle was lost. On February 1, 2003, Columbia disintegrated during re-entry over Texas, resulting in the loss of all 7 astronauts aboard. The cause was damage to the shuttle's heat shield, struck by a piece of foam that fell from the external fuel tank during launch. That small piece of foam created a hole that allowed superheated air to penetrate the wing during re-entry, leading to catastrophic failure. The accident investigations revealed flaws in NASA's safety culture, a tendency to normalize risks and downplay concerns. Once again, the shuttle fleet was grounded, this time for more than 2 years. When flights resumed, every launch was scrutinized, every piece of foam tracked, every potential risk assessed and reassessed. The shuttle program continued until 2011, when the final mission brought Atlantis home for the last time. The orbiters were retired to museums, their missions completed, their place in history secure. They had built the International Space Station, repaired the Hubble Space Telescope, and carried more than 800 people into space. But they had also claimed the lives of 14 astronauts, a reminder that reaching for the stars, the International Space Station became the next great achievement in human spaceflight. Construction began in 1998, when a Russian module called Zarya was launched, followed weeks later by the American module Unity. Over the next 13 years, piece by piece, the station was assembled in orbit, each module carried up by shuttle or rocket, each component connected by astronauts working in the vacuum of space. The ISS is a collaboration of 5 space agencies: NASA, Roscosmos, the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency, representing 15 countries working together on the most complex structure ever built in space. It is larger than a football field from end to end, weighs more than 900,000 pounds, and orbits Earth at an altitude of about 250 miles. It circles the planet once every 90 minutes, traveling at more than 17,000 miles per hour, fast enough to experience 16 sunrises and sunsets every 24 hours. Life aboard the International Space Station is a balance between routine and wonder. Astronauts and cosmonauts live there for months at a time, typically 6-month missions, though some stay longer. Their days are structured, divided into blocks of time for experiments, maintenance, exercise, and rest. They work in modules that are cramped and filled with equipment, every surface covered with handholds and restraints to keep objects from floating away. They eat from pouches and drink from bags with straws, their food prepared on Earth and sent up on cargo spacecraft. They sleep in small compartments, strapped into sleeping bags attached to the wall, because in weightlessness, there is no up or down, no mattress to lie upon. They exercise for 2 hours every day, running on a treadmill while harnessed down, cycling on a stationary bike, lifting weights that use resistance instead of gravity. This exercise is essential to prevent the loss of muscle and bone that occurs when the body no longer needs to support its own weight. The view from the ISS is breathtaking. Through the windows of the cupola, a dome-shaped module with 7 windows, astronauts can see Earth spread out below them in vivid detail. They watch storms swirl over oceans, the thin blue line of the atmosphere glowing at the horizon, the lights of cities twinkling in the darkness. They see the auroras, curtains of green and red light shimmering over the poles, caused by charged particles from the sun interacting with Earth's magnetic field. They watch the sun rise and set every 45 minutes, the Terminator line between day and night sweeping across continents. Many astronauts have spoken about the profound effect of seeing Earth from space, the way it changes their perspective, makes them more aware of the planet's fragility, the interconnectedness of all life. This feeling has been called the overview effect, a cognitive shift that comes from seeing the whole planet at once, from recognizing that borders are invisible and that the atmosphere is a thin shell protecting everything we know. Scientific research on the ISS covers a vast range of disciplines. Astronauts study how plants grow in microgravity, testing crops that could be cultivated on long-duration missions or on other planets. They observe how flames burn without gravity to pull hot air upward, creating spherical fireballs instead of the teardrop shape familiar on Earth. They conduct experiments on materials, mixing metals and compounds in ways impossible under Earth's gravity, creating alloys and crystals with unique properties. They study their own bodies, tracking how bones lose density, how muscles atrophy, how the cardiovascular system adapts to the absence of gravity's constant pull. They test new technologies, from water recycling systems that convert urine and moisture from the air into drinking water, to 3D printers that can manufacture tools and parts in orbit. The knowledge gained from these experiments informs not just future space missions, but also improves life on Earth, leading to better medical treatments, more efficient technologies, and deeper understanding of fundamental science. Spacewalks from the ISS are a regular but never routine part of station operations. Astronauts venture outside to install new equipment, replace aging components, and repair systems that cannot be maintained from inside. These extravehicular activities, as they are officially called, require extensive preparation. Astronauts spend hours pre-breathing pure oxygen to purge nitrogen from their blood, preventing the bends when they enter the lower pressure of the spacesuit. They don their suits, bulky white assemblies that weigh more than 200 pounds on Earth, but are weightless in orbit. They enter the airlock, a small chamber that can be sealed off from the rest of the station, and slowly vent the air until it matches the vacuum outside. Then they open the outer hatch and emerge into space, tethered to the station by safety lines, their suits providing oxygen, cooling, and protection from the extreme temperatures that range from boiling hot in sunlight to freezing cold in shadow. Spacewalks typically last 6 to 8 hours, during which astronauts move carefully along handrails, use specialized tools designed to work in the vacuum, and perform tasks that require both strength and delicate precision. When they finish and return inside, they close the hatch, repressurize the airlock, and remove their suits, exhausted but satisfied with the work completed. The longest continuous human presence in space is aboard the International Space Station. Since November 2nd, 2000, there has always been at least one person living in orbit, an unbroken chain of habitation now stretching more than 2 decades. Hundreds of people from more than 20 countries have visited the station, living and working together despite national differences, language barriers, and the vast distance from home. They form crews of typically 6 or 7, rotating every few months, new arrivals overlapping with those preparing to depart. This continuity represents a commitment to space exploration that goes beyond competition, a recognition that the challenges of living beyond Earth are too great for any one nation to face alone. The ISS is a symbol of what humanity can achieve when working toward a common goal, a testament to international cooperation in pursuit of knowledge. Returning to Earth from the ISS is a carefully orchestrated process. When astronauts complete their mission, they board a Soyuz spacecraft or, more recently, a SpaceX Crew Dragon capsule and undock from the station. They fire the spacecraft's engines to slow down, dropping out of orbit and beginning the descent through the atmosphere. Re-entry is intense, the friction of air against the spacecraft heating its heat shield to thousands of degrees, creating a plasma that blocks radio communication for several minutes. The crew experiences several times Earth's gravity as they decelerate, pressed back into their seats by forces they have not felt in months. Parachutes deploy to slow the final descent, and the capsule lands either on the flat steppes of Kazakhstan for Soyuz or splashes down in the ocean for Crew Dragon. When the hatch opens and the astronauts emerge, they are often unsteady on their feet, their bodies readjusting to the pull of gravity, their muscles and balance temporarily confused by the sudden return of weight. They sit in chairs while medical teams check their health, and within hours they are on their way to recovery facilities, where they will spend weeks regaining strength, relearning how to walk without stumbling, readjusting to a world that feels heavy after months of floating. Beyond Earth orbit, robotic spacecraft have extended humanity's reach farther than any astronaut has yet traveled. These missions, controlled from Earth but operating autonomously for much of their work, have visited every planet in the solar system and ventured into the space between stars. They carry cameras, instruments, and in some cases, samples of Earth itself, messages to any intelligence that might one day find them. The Voyager spacecraft, launched in 1977, took advantage of a rare alignment of the outer planets to visit Jupiter, Saturn, Uranus, and Neptune in a single grand tour. Voyager 1 flew past Jupiter and Saturn, using the gravity of each planet to slingshot onward, eventually becoming the first human-made object to enter interstellar space in 2012. Voyager 2 followed a slightly different path, becoming the only spacecraft to visit Uranus and Neptune, sending back the first and still only close-up images of those distant ice giants. Both spacecraft are now beyond the influence of the Sun's solar wind, drifting through the space between stars, their power slowly fading, but their transmitters still sending faint signals back to Earth. Attached to each Voyager is a golden record, a gold-plated copper disc containing sounds and images from Earth, a message to any civilization that might encounter them in the distant future. The golden records were the idea of astronomer Carl Sagan and a small team who worked with astonishing speed to create them before the Voyager launches. They contain 116 images encoded in analog form, showing scenes from Earth, people of different cultures, landscapes, animals, and diagrams explaining the location of our solar system. There are greetings spoken in 55 languages, from ancient Akkadian to modern Chinese, each a simple hello from Earth. There is a selection of music, 90 minutes of songs from around the world, from Bach, Beethoven, from traditional music of many cultures to Chuck Berry. There is a recording of natural sounds, thunder, wind, birds, whales, the cry of a baby, the beat of a human heart. And there is a message from President Jimmy Carter, expressing the hope that the records might one day be found and that they would communicate something of who we are. The records were designed to last billions of years, protected from cosmic radiation and micrometeorite impacts by their covers, waiting in the silence of space for a discovery that may never come, but represents a hope that we are not alone, that someone, somewhere, might find this gift from a distant world and know that we reached out. Mars has become the focus of robotic exploration in recent decades. Beginning with flybys and orbiters in the 1960s and 70s, missions to Mars have grown steadily more sophisticated, culminating in rovers that drive across the surface, analyzing rocks, drilling into soil, and searching for signs that the planet might once have harbored life. The first successful Mars rover, Sojourner, was a small six-wheeled vehicle about the size of a microwave oven, deployed from the Mars Pathfinder lander in 1997. It spent nearly 3 months exploring a small area around the landing site, testing how a rover could navigate Martian terrain. Sojourner's success paved the way for larger and more capable rovers. Spirit and Opportunity landed on opposite sides of Mars in January 2004, each designed to operate for 90 days. Instead, they functioned for years, Spirit until 2010 and Opportunity until 2018. They drove for miles across the Martian surface, climbing hills, exploring craters, finding evidence that water once flowed on Mars, that ancient lakes and rivers once existed where now there is only dust and rock. Curiosity, the largest rover to land on Mars at the time, arrived in August 2012, lowered to the surface by a sky crane that used retro rockets to hover while cables gently set the rover down. Curiosity is the size of a small car, equipped with a suite of scientific instruments that allow it to analyze the chemistry of rocks, search for organic molecules, and assess whether the environment at Gale Crater could ever have supported microbial life. It carries a drill on its robotic arm that can bore into rocks and collect samples for analysis inside the rover. It has cameras that can take high-resolution panoramas in color, capturing the stark beauty of the Martian landscape, the layered sediments of Mount Sharp rising in the distance, the ancient riverbeds carved into the crater floor. Curiosity has been exploring Mars for more than a decade, driving slowly but steadily, sending back images and data that have reshaped our understanding of the planet's history. It has found evidence of ancient habitable environments, places where water, energy, and the chemical ingredients for life all existed together. Though whether life actually arose remains an open question. Perseverance, the most recent and advanced rover, landed in Jezero Crater in February 2021. It is similar in size to Curiosity, but carries different instruments focused on a new goal: searching for signs of ancient microbial life and collecting samples that could one day be returned to Earth. Perseverance carries a small drill that can collect core samples of rock and seal them in tubes, which it then deposits at carefully chosen locations on the surface. Future missions, still in the planning stages, would retrieve these samples, launch them into Martian orbit, and bring them back to Earth, where they could be studied in laboratories with instruments far more capable than anything that can be sent to Mars. The rover also carries a small helicopter named Ingenuity, a technology demonstration designed to prove that powered flight is possible in Mars's thin atmosphere. Ingenuity made its first flight in April 2021, hovering for just under 40 seconds, a few feet above the ground. It has since completed dozens of flights, scouting ahead of the rover, demonstrating capabilities that will be essential for future missions that might use aerial vehicles to explore areas that rovers cannot reach. The journey to Mars takes about 6 to 9 months, depending on the alignment of the planets. Spacecraft launched when Earth and Mars are positioned to minimize travel time and fuel requirements, a window that opens roughly every 26 months. During the journey, the spacecraft coasts through the void, making small course corrections, but mostly relying on the initial boost from the launch rocket. There is no turning back, no way to slow down or change course significantly once the trajectory is set. The landing is the most dangerous part, a sequence of events that NASA engineers have called the 7 minutes of terror, the time between entering the Martian atmosphere and touching down on the surface. In those 7 minutes, the spacecraft must decelerate from more than 12,000 miles per hour to 0, using a combination of heat shield, parachute, and retro rockets. Communication with Earth is delayed by the distance, signals taking anywhere from 4 to 24 minutes to travel each way, depending on where the planets are in their orbits. This means the landing is entirely automated, following pre-programmed instructions with no possibility of real-time control from mission operators. They can only watch the telemetry as it arrives, learning what happened minutes after the fact, hoping that each step executed as planned. Every successful Mars landing has been a triumph of engineering and precision. The rovers have landed in different regions of the planet, chosen for their scientific interest, their potential to reveal Mars's history and climate. Spirit and Opportunity explored areas where ancient water left its mark, finding minerals that form only in the presence of water, discovering evidence of acidic lakes and groundwater systems. Curiosity studies the layers of sediment at the base of Mount Sharp, reading them like pages in a book that tell the story of how the climate changed over millions of years, from a warmer, wetter world to the cold desert it is today. Perseverance explores Jezero Crater, the site of an ancient river delta, where water once flowed into a lake, carrying sediments and organic material that might have preserved traces of ancient life if it ever existed. Each rover adds to the growing body of knowledge, each image and measurement a piece of the puzzle that is slowly revealing what Mars was and whether it might still harbor life beneath its surface. The human exploration of Mars remains a goal for the future, a challenge that will require new technologies, new spacecraft, and a level of commitment and resources far greater than anything attempted so far. Sending astronauts to Mars means solving problems that have no easy answers. The journey is long, at least 6 months in each direction, exposing crew members to cosmic radiation and the debilitating effects of prolonged weightlessness. The spacecraft would need to carry enough supplies to sustain the crew for the entire mission, including the time spent on the surface, which would likely be at least a year to wait for Earth and Mars to align properly for the return journey. Life support systems would need to recycle air and water with near-perfect efficiency, since resupply from Earth would be impossible. The landing would be more complex than anything yet attempted, requiring spacecraft large enough to carry people and supplies, but capable of slowing down in Mars's thin atmosphere. And once on the surface, astronauts would face an environment hostile in every way, with temperatures far below freezing, an atmosphere that is mostly carbon dioxide and too thin to breathe, and dust storms that can cover the entire planet. Despite these challenges, plans for human missions to Mars are being developed. NASA's Artemis program aims to return astronauts to the Moon as a stepping stone, using lunar missions to test technologies and procedures that will be needed for Mars. The Moon is only 3 days away, close enough that help can be sent if something goes wrong, close enough that communication delays are measured in seconds, not minutes. By establishing a sustainable presence on the Moon, building habitats, and learning to live off the land, by extracting water from ice in permanently shadowed craters, and using it to produce oxygen and rocket fuel, space agencies hope to develop the capabilities that will make Mars missions feasible. Private companies are also working toward Mars, designing heavy-lift rockets capable of carrying large payloads, developing spacecraft that could transport crews across interplanetary space, and envisioning settlements where humans might one day live. These plans are ambitious. Some would say audacious, but they represent the continuation of the same impulse that drove Gagarin into orbit, Armstrong onto the Moon, and rovers across the Martian surface. The desire to explore, to expand our horizons, to become a species that is not confined to a single world. The history of space travel is a story of incremental progress, of small steps that accumulate into giant leaps. It is a story of people who dedicated their lives to solving problems that had never been solved before, who built machines capable of withstanding the vacuum of space, the heat of re-entry, the cold of the outer solar system. It is a story of astronauts and cosmonauts who climbed into capsules knowing the risks, who trusted their training and their colleagues, who looked back at Earth and saw it as a single, fragile home. It is a story of missions that succeeded beyond expectation and missions that failed despite every precaution, each teaching lessons that made the next attempt safer, smarter, better. From the first satellite, Sputnik 1, launched by the Soviet Union in 1957, to the rovers currently exploring Mars, humanity has been reaching outward for more than 60 years, learning, adapting, and persisting in the face of challenges that once seemed insurmountable. The technology that makes space travel possible has transformed life on Earth as well. Satellites in orbit provide weather forecasting that saves lives by predicting hurricanes and storms days in advance. They enable global positioning systems that have become essential for navigation, communication networks that connect even the most remote corners of the planet, and Earth observation systems that monitor climate, deforestation, ocean health, and countless other variables essential to understanding our world. The miniaturization of electronics, driven by the need to reduce weight and power consumption in spacecraft, has led to advances that power our phones, computers, and countless devices we use every day. Materials developed for space, from heat-resistant ceramics to lightweight composites, are used in everything from firefighting equipment to sports gear. Medical imaging techniques, refined for monitoring astronaut health, have improved diagnostics on Earth. Water purification systems, designed for the ISS, are being used to provide clean drinking water in developing regions. The pursuit of space has yielded benefits far beyond the immediate goals of exploration. Yet, the most profound impact of space travel may be the perspective it offers. The images of Earth from space, from the first grainy black and white photographs to the high-definition videos streaming from the ISS, have changed how we see ourselves. They reveal a planet without borders, a world where the atmosphere is a thin, fragile layer, where oceans and continents form a single interconnected system, where all of humanity shares a common home. Astronauts who have seen this view often speak of a sense of unity, recognition that the divisions we create among ourselves are trivial compared to the vastness of space and the preciousness of the one planet we inhabit. This perspective, this awareness of our place in the cosmos, may be the greatest gift that space travel has given us. It reminds us that we are explorers by nature, curious and restless, always looking beyond the next horizon. But it also reminds us that we carry a responsibility to protect the world that made us, to preserve it for those who will come after, to ensure that future generations can look up at the stars and dream of reaching them just as we have done. The technologies developed for space travel have transformed life on Earth in ways both obvious and subtle. Satellite technology, which began as an offshoot of rocket development, has become indispensable. Weather satellites orbit Earth continuously, tracking storms, monitoring ocean temperatures, measuring atmospheric conditions. Their data feeds into models that forecast weather days in advance, saving lives by predicting hurricanes, tornadoes, and severe storms. Before satellites, weather forecasting was largely guesswork beyond a day or two. Now, meteorologists can see weather systems developing across entire hemispheres, watch them evolve, and provide warnings that give people time to prepare or evacuate. This capability has saved countless lives and prevented enormous economic damage. Communication satellites have revolutionized how information travels. Instead of relying on cables stretched across oceans or limited radio transmissions, signals can be bounced off satellites in geostationary orbit, reaching anywhere on Earth almost instantaneously. This enables global television broadcasts, international phone calls, internet connectivity in remote regions. The modern world's interconnectedness, the ability to communicate across continents in real time, relies on networks of satellites that trace their origins to the early space programs. Navigation satellites form another critical infrastructure. The Global Positioning System, or GPS, consists of a constellation of satellites that continuously broadcast timing signals. Receivers on the ground use these signals to determine their precise location, accurate to within a few feet. GPS has become so embedded in daily life that it is easy to forget it is a space-based technology. It guides airplanes, ships, and cars, enables precise mapping, supports emergency services, and powers countless applications on smartphones. Earth observation satellites monitor the planet's health and change over time. They track deforestation, measure ice sheet thickness in polar regions, observe coral reef degradation, monitor air and water quality. Scientists use this data to study climate change, to understand how human activities affect ecosystems, to track the spread of diseases, to respond to natural disasters. When a wildfire ignites, satellites detect it quickly, allowing firefighters to respond before it spreads. When an earthquake strikes, satellites can assess damage to buildings and infrastructure, helping coordinate rescue efforts. The view from orbit provides a perspective that ground-based observation cannot match, revealing patterns and connections that are invisible from the surface. Yet the story of human spaceflight extends far beyond the missions we have explored so far. Before the International Space Station became humanity's permanent outpost in orbit, other space stations paved the way, teaching lessons that would prove essential for long-duration spaceflight. The story of space stations begins decades before the International Space Station, in an era when the idea of permanent human presence in orbit was still being imagined and tested. The Soviet Union launched the world's first space station on April 19, 1971. Called Salyut-1, meaning salute in Russian, it was a cylinder-shaped structure about 65 feet long and 13 feet wide at its widest point, roughly the size of a large bus. It had 3 pressurized compartments where cosmonauts could live and work, solar panels extending like wings to capture sunlight and convert it to electricity, and a single docking port where Soyuz spacecraft could attach to deliver crews. Salyut-1 was designed to test whether humans could live in space for extended periods, whether they could conduct scientific experiments in orbit, whether the systems needed to support life could function reliably for weeks or months. It was an ambitious step forward, transforming spaceflight from brief journeys into longer stays where astronauts would sleep, eat, and work in microgravity, adapting to an environment that challenged every assumption about how to live. The first attempt to cruise Salyut 1 ended in disappointment. Soyuz 10 launched on April 23rd, carrying 3 cosmonauts who successfully reached the station and achieved what is called a soft dock, where the spacecraft touched the docking mechanism. But the hard dock, the secure connection that would allow them to open hatches and enter the station, failed. Despite their efforts, the crew could not establish a solid link. After struggling for hours, they had to give up and return to Earth, their mission incomplete. The failure was frustrating, a reminder that even carefully planned procedures could go wrong in the unforgiving environment of space. But it also provided valuable data, helping engineers understand what needed to change in the docking system. 3 weeks later, Soyuz 11 launched with a replacement crew, cosmonauts Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev. This time, the docking succeeded. The hatches opened, and the 3 men floated into Salyut 1, becoming the first people to enter a space station. The crew of Soyuz 11 spent 23 days aboard Salyut 1, a record at the time. They conducted experiments, tested the station's systems, adjusted to the rhythms of life in orbit. They grew plants, operated the Orion 1 space telescope to observe stars in ultraviolet wavelengths, invisible from Earth's surface, and studied how their bodies adapted to weightlessness. They spoke with ground control, sent reports, and described what it was like to live in this new kind of spacecraft, one not designed for a brief flight, but for ongoing habitation. The mission seemed to be a success, a milestone that proved humans could establish a presence beyond Earth. When the time came to return, the crew packed their equipment, sealed the hatches, and climbed into their Soyuz spacecraft. They undocked from Salyut 1 and began the descent back to Earth. But during re-entry, a pressure valve malfunctioned, opening prematurely and venting the cabin's atmosphere into the vacuum of space. The cosmonauts were not wearing spacesuits, following the standard procedure at the time. Within seconds, they lost consciousness. By the time the capsule landed, all 3 had passed. The tragedy of Soyuz 11 cast a shadow over the early days of space stations. It was the first, and remains the only time that humans have lost their lives in the vacuum of space itself, not during launch or landing, but during the journey between. The Soviet space program halted crewed flights for more than a year, while engineers redesigned the Soyuz spacecraft, making changes to prevent such an accident from ever happening again. Future crews would wear spacesuits during launch and re-entry, a requirement that continues to this day. The Salyut program continued despite the loss, but the setback was profound. Salyut 1 was deorbited in October 1971, its fuel exhausted, its mission cut short. It burned up over the Pacific Ocean, leaving behind lessons written in tragedy and triumph. A first step toward the space stations that would. Over the next decade, the Soviet Union launched 6 more Salyut stations, each an improvement on the last. Some were scientific stations designed for research in physics, astronomy, biology. Others were military stations, part of a program called Almaz, used for reconnaissance and observation. Salyut 2 suffered a catastrophic failure shortly after reaching orbit and was never occupied. Salyut 3 and 5 were the military variants, hosting crews who conducted classified observations and experiments. Salyut 4 was a civilian station that spent more than 4 years in orbit, visited by two long-duration crews who set new records for time in space. Each mission taught the Soviets more about how to sustain humans in orbit, how to resupply stations with cargo spacecraft, how to manage the psychological and physical challenges of living in such a confined and isolated environment. Salyut 6 and 7 represented the next generation, stations with two docking ports instead of one, allowing them to be resupplied while still hosting a crew. This innovation extended their operational lifetimes significantly. Salyut 6, launched in 1977, remained in orbit for nearly 5 years, hosting 16 crews. Cosmonauts stayed for months at a time, the longest mission lasting 185 days. They conducted extensive scientific research, grew crystals in microgravity, studied Earth's oceans and atmosphere, operated telescopes to observe distant galaxies. Salyut 6 also welcomed international visitors, cosmonauts from allied nations who joined Soviet crews in a gesture of cooperation. The station became a proving ground for long-duration spaceflight, demonstrating that humans could live in orbit not just for weeks, but for many months, adapting, working, and even thriving in an environment far from home. Salyut 7, launched in 1982, continued this legacy. It was designed as a backup for Salyut 6, but became its own successful station, hosting 11 crews over nearly 5 years. The station featured improved living conditions, ergonomic furniture, hot water, a refrigerator, even window shades to block sunlight during sleep periods. Cosmonauts grew plants that flowered in space for the first time, small green shoots that demonstrated life's resilience beyond Earth. In 1985, while unmanned, Salyut 7 suffered a complete power failure. Its electrical systems shut down, communication with the ground was lost, and the station began tumbling slowly through space. It seemed doomed. But two cosmonauts, Vladimir Janibekov and Viktor Savinik, launched on a daring rescue mission. They docked with the non-functional station, entered its dark and freezing interior, and spent weeks diagnosing and repairing the electrical systems. Their success in bringing Salyut 7 back to life was a testament to human ingenuity and determination, proving that even seemingly catastrophic failures could be overcome with skill and. The experience gained from the Salyut program laid the foundation for Mir, the Soviet Union's crowning achievement in space station development. Launched in February 1986, Mir was the first modular space station, designed to be assembled piece by piece in orbit. The core module, which formed the heart of the station, resembled the Salyut stations, but was equipped with 6 docking ports, allowing additional modules and visiting spacecraft to attach from multiple directions. Over the next 10 years, 5 more modules were added, each bringing specialized capabilities. Kvant 1 carried telescopes and detectors for astrophysics research. Kvant 2 provided additional living space, an airlock for spacewalks, and systems for recycling water. Crystal held furnaces for materials science experiments and a docking port designed for the Soviet Buran space shuttle, though that shuttle program was cancelled before any Buran ever visited Mir. Spectre and Priroda, added in the 1990s, brought more scientific instruments and equipment for Earth observation and atmospheric studies. Mir was larger and more complex than any previous station, stretching more than 100 feet from end to end when all modules were attached, with a mass of more than 130 tons. It was home to cosmonauts for 15 years, an uninterrupted occupation that saw crews rotate every few months, new arrivals overlapping with those preparing to depart. More than 100 people from 12 countries lived aboard Mir during its operational life, including astronauts from the United States, France, Germany, and other nations. The station became a symbol of international cooperation, especially after the Cold War ended and former rivals began working together in space. The Shuttle Mir program, a series of missions in the mid-90s, saw American space shuttles dock with Mir, delivering astronauts who stayed for months at a time, conducting joint research and building the relationships that would later form the foundation for the International Space Station. Life aboard Mir was challenging in ways both predictable and surprising. The station was cramped, its modules filled with equipment, cables, and supplies that left little room to move. The air was often stale, recycled through scrubbers that removed carbon dioxide but could not eliminate all odors. Noise from fans and pumps was constant, a background hum that cosmonauts learned to ignore or sleep through. Exercise was essential to prevent muscle and bone loss, but the equipment was basic: treadmills and resistance devices that required discipline to use every day. Food was pre-packaged, sent up on cargo ships, much of it freeze-dried or canned, flavors dulled by the inability to smell properly in microgravity. Yet cosmonauts adapted. They found ways to personalize their sleeping quarters, brought small tokens from home, photographs of family, favorite books, music. They celebrated birthdays and holidays, shared meals, told stories. They looked out the windows at Earth turning below, at the stars beyond, and found meaning in the work they were doing. Mir experienced its share of crises. In 1997, a fire broke out in the Kvant-1 module when a faulty oxygen generator ignited. Flames spread quickly in the oxygen-rich environment, filling the station with smoke and heat. The crew fought the fire for several minutes, using extinguishers and finally managing to smother it. No one was seriously hurt, but the incident highlighted the dangers of living in a sealed environment where fire cannot simply be escaped. Later that same year, an unmanned Progress cargo ship collided with Mir during a docking test, puncturing the Spectre module and causing a rapid loss of air pressure. The crew quickly sealed off the damaged module, abandoning it to the vacuum and preserving the rest of the station. Repairs were made during subsequent spacewalks, but Spectre was never fully restored. These incidents were sobering reminders that space stations are fragile, that survival depends on quick thinking, training, and a measure of luck. Despite the challenges and occasional disasters, Mir's scientific legacy is substantial. Cosmonauts conducted experiments that could only be done in microgravity, studying how flames burn without convection, how crystals grow in the absence of gravitational settling, how plants orient themselves without a clear up or down. They tested new materials, observed Earth's climate and ecosystems, monitored their own bodies to understand the long-term effects of spaceflight. Cosmonaut Valery Polyakov spent 437 consecutive days aboard Mir, setting a record for the longest single spaceflight that still stands. His mission provided invaluable data on how the human body and mind cope with isolation and confinement for more than a year, information that will be essential for future missions to Mars and beyond. When Mir was finally deorbited in March 2001, guided into a controlled re-entry over the Pacific Ocean, it left behind a legacy that continues to shape how we think about living in space. The design and operation of Mir directly influenced the International Space Station. The modular approach, the emphasis on international cooperation, the lessons learned from years of continuous habitation all became part of the ISS's foundation. The Russian segments of the ISS, including the Zvezda service module, trace their lineage directly back to the Salyut and Mir programs. Zvezda, which provides life support, living quarters, and docking ports for the Russian side of the station, is essentially a descendant of the Mir core module, incorporating decades of refinement and improvement. The continuity is clear, a thread running from the first Salyut station through Mir to the present day, a testament to the value of incremental progress, of building on what has been learned rather than starting from scratch. Spacewalks, those moments when astronauts leave the safety of their spacecraft and work directly in the vacuum, have been a critical part of space exploration since the earliest days. The first human to perform a spacewalk was Soviet cosmonaut Alexei Leonov. On March 18, 1965, during the Voskhod 2 mission, Leonov opened the airlock and floated outside for 12 minutes and 9 seconds. It was a moment of profound significance, the first time a human had ventured into the void with nothing but a spacesuit for protection. But the spacewalk was far more difficult than anyone anticipated. Leonov's suit ballooned in the vacuum, stiffening to the point where he could barely move his limbs. He struggled to operate the camera mounted on his chest, unable to bend enough to press the shutter. When it came time to return to the spacecraft, he found that his suit had expanded so much he could not fit back through the airlock. In a desperate decision, he partially vented his suit, reducing the pressure just enough to squeeze through. The procedure was dangerous, risking decompression sickness, but it worked. Leonov emerged from the experience overheated, exhausted, and triumphant, having proven that humans could survive outside a spacecraft, though just barely. The first American spacewalk followed less than 3 months later. On June 3, 1965, astronaut Ed White floated outside the Gemini 4 capsule for 23 minutes. Unlike Leonov, White was equipped with a handheld maneuvering unit, a small gun that expelled jets of compressed gas, allowing him to move and orient himself more freely. White described the experience as exhilarating, the view of Earth from outside the capsule breathtaking in a way that no words could fully capture. When Mission Control ordered him back inside, he famously replied that it was the saddest moment of his life. White's spacewalk was successful, but it also revealed challenges. Moving in the suit required more effort than expected, and the simple act of closing the hatch afterward proved difficult, delaying their return inside. These early spacewalks taught engineers and astronauts alike that working in space demanded new techniques, new tools, and extensive training. The Gemini program conducted several more spacewalks, each teaching important lessons. Gene Cernan's EVA on Gemini 9 was particularly difficult. He was supposed to test a maneuvering backpack stowed at the rear of the spacecraft. But without adequate handholds to stabilize himself, Cernan struggled, his heart rate soaring, his visor fogging from exertion and sweat. He became so overheated and exhausted that the mission had to be cut short. His experience led to the realization that astronauts needed better ways to anchor themselves while working, that tasks which seemed simple on paper were brutally difficult in the reality of microgravity. The final Gemini mission, Gemini 12, flown by Buzz Aldrin, incorporated these lessons. Aldrin spent more than 5 hours outside during multiple EVAs, moving methodically, using newly installed handholds and foot restraints. He also trained extensively underwater, a technique that simulates the floating sensation of microgravity and allows astronauts to practice movements without the complexity of spaceflight. Aldrin's successful spacewalks demonstrated that with proper preparation and equipment, EVAs could be productive and sustainable. Spacewalks became routine during the Apollo moon landings, though those were surface EVAs rather than ones conducted in orbit. Astronauts walked on the lunar surface in bulky suits designed to withstand the extremes of the moon's environment. suits that provided oxygen, cooling, and protection from micrometeorites and radiation. The Apollo spacesuits were marvels of engineering, allowing astronauts to bend, kneel, and work, despite the stiffness caused by the internal pressure that kept them alive. Each moonwalk added to the understanding of how humans could function beyond Earth, how they could explore, collect samples, deploy instruments, and operate vehicles in an environment completely alien to their evolution. When the Apollo program ended and attention shifted to space stations, spacewalks took on new purposes, focused on construction, maintenance, and repair rather than exploration. The space shuttle era brought a new kind of spacewalk. Astronauts working from the shuttle conducted EVAs to deploy satellites, capture malfunctioning spacecraft, and bring them into the cargo bay for repair, and later to build the International Space Station. The shuttle's cargo bay could be depressurized and opened to space, providing a large work area from which astronauts could operate. The Extravehicular Mobility Unit, or EMU, the spacesuit used by shuttle and ISS astronauts, became a sophisticated piece of equipment, essentially a wearable spacecraft. It includes layers of insulation, a hard upper torso that houses life support systems, gloves with heaters to keep fingers warm, a helmet with a gold-plated visor to reflect sunlight and protect against radiation. Inside the suit, astronauts breathe pure oxygen at lower pressure than the station's interior, which requires them to pre-breathe for hours before an EVA to purge nitrogen from their blood and prevent decompression sickness. One of the most famous spacewalks in history occurred in February 1984 during a shuttle mission. Astronaut Bruce McCandless ventured out wearing a manned maneuvering unit, a backpack equipped with small nitrogen thrusters that allowed him to fly freely without being tethered to the spacecraft. He floated more than 300 feet away from the shuttle, the first human to be completely untethered in space. Photographs from that EVA show McCandless as a tiny white figure against the black void, Earth's blue curve far below, the shuttle a distant shape in the background. The image is both beautiful and terrifying, a stark illustration of the vastness of space and the smallness of a human within it. The MMU was used on only a few missions before being retired, deemed too risky for regular use, but it remains a symbol of the audacious possibilities of spacewalking. Building the International Space Station required hundreds of hours of EVA time. From 1998 to the station's completion in 2011, astronauts and cosmonauts conducted more than 160 spacewalks to assemble modules, install equipment, connect cables, and deploy solar arrays. These EVAs were meticulously planned, every movement choreographed in advance, every tool selected and tethered to prevent it from floating away. Astronauts moved slowly and deliberately, aware that a mistake could damage critical systems or endanger their lives. They worked in pairs, one performing the task while the other provided assistance and monitored safety. Communication with mission control was constant, engineers on the ground guiding them through procedures, offering advice, watching telemetry to ensure that suit systems functioned properly. Spacewalks from the ISS typically last 6 to 8 hours, limited by the capacity of the suit's batteries and the physical endurance of the astronauts. Working in a spacesuit is exhausting, the hands growing sore from gripping tools through thick gloves, the body straining against the resistance of the suit's pressurized joints. Astronauts train for months before their EVAs, spending hours in the Neutral Buoyancy Laboratory, a massive pool at NASA's Johnson Space Center, where full-scale mock-ups of ISS modules are submerged. In the pool, astronauts practice the tasks they will perform in space, moving through procedures until they become second nature. They learn to conserve energy, to work efficiently, to recognize when they are pushing too hard and need to rest. The training is so thorough that by the time they perform the actual spacewalk, the movements feel familiar, almost routine, despite the extraordinary environment. The risks of spacewalking are real and ever-present. In 2013, Italian astronaut Luca Parmitano experienced a potentially critical malfunction during an EVA. Water began leaking into his helmet from the suit's cooling system, pooling around his face. In microgravity, water does not drip down. It clings to surfaces, spreading like a growing puddle. Parmitano's vision became obscured. Then water covered his nose and mouth, making it difficult to breathe. He remained calm, following procedures, while his crewmate and mission control worked urgently to get him back inside the airlock. The EVA was aborted, and Parmitano made it back safely. But the incident highlighted how quickly a minor malfunction can escalate into a life-threatening emergency. The suits were subsequently redesigned to prevent similar leaks, another example of how spaceflight continually evolves through experience, both successful and harrowing. Despite the dangers, spacewalks continue to be essential for maintaining the ISS and will be crucial for future missions. Plans for returning to the Moon include extensive EVAs to set up habitats, deploy equipment, and explore the lunar surface in greater detail than Apollo astronauts could. Mars missions, if and when they occur, will require spacewalks in a new environment, with different gravity, different atmospheric pressure, and different challenges. Each location demands adaptations in suit design, procedures, and training. The knowledge accumulated from decades of spacewalks, from Leonov's pioneering first steps to the routine EVAs conducted today, forms a foundation that will support human exploration wherever it goes next. The technologies developed for space travel have transformed life on Earth in ways both obvious and subtle. Satellite technology, which began as an offshoot of rocket development, has become indispensable. Weather satellites orbit Earth continuously, tracking storms, monitoring ocean temperatures, measuring atmospheric conditions. Their data feeds into models that forecast weather days in advance, saving lives by predicting hurricanes, tornadoes, and severe storms. Before satellites, weather forecasting was largely guesswork beyond a day or two. Now, meteorologists can see weather systems developing across entire hemispheres, watch them evolve, and provide warnings that give people time to prepare or evacuate. This capability has saved countless lives and prevented enormous economic damage. Communication satellites have revolutionized how information travels. Instead of relying on cables stretched across oceans or limited radio transmissions, signals can be bounced off satellites in geostationary orbit, reaching anywhere on Earth almost instantaneously. This enables global television broadcasts, international phone calls, internet connectivity in remote regions. The modern world's interconnectedness, the ability to communicate across continents in real time, relies on networks of satellites that trace their origins to the early space programs. Navigation satellites form another critical infrastructure. The Global Positioning System, or GPS, consists of a constellation of satellites that continuously broadcast timing signals. Receivers on the ground use these signals to determine their precise location, accurate to within a few feet. GPS has become so embedded in daily life that it is easy to forget it is a space-based technology. It guides airplanes, ships, and cars, enables precise mapping, supports emergency services, and powers countless applications on smartphones. Earth observation satellites monitor the planet's health and change over time. They track deforestation, measure ice sheet thickness in polar regions, observe coral reef degradation, monitor air and water quality. Scientists use this data to study climate change, to understand how human activities affect ecosystems, to track the spread of diseases, to respond to natural disasters. When a wildfire ignites, satellites detect it quickly, allowing firefighters to respond before it spreads. When an earthquake strikes, satellites can assess damage to buildings and infrastructure, helping coordinate rescue efforts. The view from orbit provides a perspective that ground-based observation cannot match, revealing patterns and connections that are invisible from the surface. The miniaturization of electronics, driven by the need to reduce weight and power consumption in spacecraft, has led to technologies that permeate modern life. Early spacecraft required compact, reliable computers capable of functioning in the harsh environment of space. The development of integrated circuits, microprocessors, and later microchips accelerated because of these demands. The same technologies that allowed Apollo astronauts to navigate to the moon now power smartphones, laptops, and countless other devices. The materials science developed for space has produced innovations used on Earth. Heat-resistant ceramics, created to protect spacecraft during re-entry, are used in firefighting gear and industrial furnaces. Lightweight composite materials designed for rockets and satellites are found in everything from bicycles to aircraft to sports equipment. Memory foam, originally developed to improve seat cushioning and crash protection in spacecraft, is now widely used in mattresses and pillows. Medical technologies have also benefited from space research. Devices developed to monitor astronaut health in orbit have been adapted for use in hospitals, providing continuous, non-invasive monitoring of vital signs. Imaging techniques refined for analyzing data from space telescopes have improved medical diagnostics, allowing doctors to see inside the body with greater clarity. Water purification systems, designed for the ISS, which recycle urine and moisture from the air into drinkable water with remarkable efficiency, have been adapted to provide clean water in developing regions and disaster zones where traditional infrastructure is unavailable. The challenges of keeping astronauts healthy in space have led to advances in nutrition, exercise physiology, and telemedicine that improve healthcare for everyone. The environmental movement has been profoundly influenced by images from space. The photographs of Earth, taken during the Apollo missions, particularly the iconic Earthrise image from Apollo 8 and the blue marble photograph from Apollo 17, changed how people see the planet. These images show Earth as a whole, a single, interconnected system, fragile and beautiful, suspended in the blackness of space. There are no visible borders, no distinctions between nations, just oceans, continents, clouds, and the thin blue line of the atmosphere. Seeing Earth from this perspective fosters a sense of unity and responsibility, an awareness that all of humanity shares a common home and a common destiny. This shift in perspective, often called the overview effect, has inspired environmental movements, shaped policies, and influenced how people think about sustainability and stewardship of the planet. The economic impact of space exploration is substantial. The space industry employs hundreds of thousands of people around the world, from engineers and scientists to technicians and support staff. It drives innovation, creates new markets, and generates technologies that have applications far beyond their original purpose. Satellites alone represent a multi-billion-dollar industry, with commercial companies launching constellations for communications, Earth observation, and navigation. The development of reusable rockets by companies like SpaceX has reduced the cost of access to space, opening opportunities for new players and new applications. Space tourism, once the realm of science fiction, is becoming a reality, with private companies offering suborbital flights to paying customers and planning orbital hotels for the future. While controversial and expensive, these ventures represent a broadening of who can go to space, a shift from government astronauts to private citizens, from exploration driven by national goals to commercial ventures pursuing profit and adventure. The inspiration provided by space exploration is perhaps its most intangible but profound impact. When people watch a rocket launch, when they see images from Mars or the ISS, when they hear stories of astronauts living in orbit, it sparks imagination and curiosity. Children dream of becoming astronauts, engineers, scientists. Students pursue careers in science and technology because they were inspired by what humanity has achieved in space. The challenges of reaching the moon, of building space stations, of sending robots to other planets, demonstrate what is possible when people work together toward a common goal. They show that difficult problems can be solved, that ambitious dreams can be realized, that the limits of what we can do are often self-imposed rather than absolute. This inspiration ripples through society, encouraging innovation, fostering a culture of exploration and discovery, reminding people that there is always more to learn, more to achieve, more to wonder about. The journey to Mars, still in the planning stages, represents the next great challenge. Unlike the Moon, Mars is far enough away that the trip takes months, and communication delays can be as long as 20 minutes each way. A mission to Mars would need to be largely self-sufficient, with the crew solving problems on their own, because waiting for instructions from Earth would not always be practical. The spacecraft would need to carry enough supplies for the entire journey, including the time spent on the surface, which would likely be a year or more, to wait for the planets to align properly for the return trip. This means recycling air and water with near-perfect efficiency, growing food to supplement stored rations, and managing the psychological toll of isolation in a confined space for years. Radiation is one of the biggest challenges. Beyond Earth's protective magnetic field and atmosphere, astronauts are exposed to cosmic rays and solar radiation that increase the risk of cancer and other health problems. The spacecraft would need shielding, but adding too much mass makes the mission prohibitively expensive and difficult to launch. Researchers are exploring various solutions, from water-filled walls that provide radiation protection while also serving as a supply of drinking water, to magnetic fields generated by the spacecraft to deflect charged particles. Another approach is to simply make the journey as short as possible, using more powerful propulsion systems to reduce travel time and exposure. The landing on Mars presents unique difficulties. The planet's atmosphere is thin, only about 1% the density of Earth's, which makes it difficult to slow down using parachutes alone. But it is thick, enough to cause friction and heat during entry. Spacecraft must use a combination of heat shields, parachutes, and retro rockets, a complex sequence that must be executed perfectly. The terrain is varied, from flat plains to steep canyons, from fields of boulders to slopes covered in fine dust. Choosing a safe landing site that is also scientifically interesting requires detailed knowledge of the surface, gathered by orbiters and previous missions. The descent must be automated because the communication delay makes real-time control impossible. Engineers can only watch and hope, knowing that by the time they see the data, the landing has already succeeded or failed. Once on the surface, astronauts would face an environment hostile in every way. Temperatures can drop to more than 100 degrees below zero at night, even in the summer. The atmosphere is mostly carbon dioxide, unbreathable, with pressure so low that water boils at room temperature. Dust storms can cover the entire planet, blocking sunlight for weeks. The soil contains perchlorates, toxic chemicals that would be harmful if ingested or breathed. Astronauts would spend most of their time in habitats, pressurized modules that provide breathable air, comfortable temperatures, and protection from radiation. They would venture outside only in spacesuits, conducting exploration, collecting samples, setting up experiments. The suits would need to be more durable than those used on the ISS, capable of withstanding abrasive dust and the sharp edges of volcanic rock. Despite the challenges, the vision of humans walking on Mars captures the imagination. It represents a continuation of the same impulse that drove early explorers to cross oceans, climb mountains, venture into unknown lands. Mars is not simply another destination. It is a world that might once have been more like Earth, with rivers, lakes, perhaps even oceans. Understanding what happened to Mars, why it changed from a potentially habitable world to the cold desert it is today, could teach us about the fragility of planetary climates, about the factors that make a world capable of supporting life. And there is always the tantalizing possibility that life might still exist on Mars, hidden in subsurface ice or deep underground where conditions are less harsh. Finding evidence of life, even microbial life, on another planet would be one of the most profound discoveries in history, answering a question that humanity has pondered for as long as we have looked up at the stars and wondered if we are alone. The technologies being developed for Mars missions have applications closer to home. Advanced life support systems, more efficient solar panels, better radiation shielding, techniques for growing food in confined spaces, all of these could benefit life on Earth. The process of preparing for Mars is driving innovation, pushing engineers and scientists to solve problems in new ways. The lessons learned will make future missions safer and more capable, whether those missions are to the Moon, to asteroids, or eventually beyond Mars to the moons of Jupiter and Saturn. Worlds like Europa and Enceladus that hide oceans beneath their icy crusts and might harbor conditions suitable for life. The history of space travel is a story of continuity, each generation building on what came before. From Gagarin's single orbit to the continuous presence aboard the ISS, from the first tentative spacewalks to routine EVAs, from robotic probes that barely reach the Moon to rovers exploring Mars, the progression is clear. Each achievement expanded what was possible. Each setback taught lessons that made the next attempt stronger. The astronauts and cosmonauts who risked their lives, the engineers who solved impossible problems, the scientists who asked bold questions, all contributed to a growing body of knowledge and capability that defines human spaceflight. This is not a story with an ending. It is an ongoing narrative, a journey that continues, driven by curiosity, ambition, and the belief that our place is not limited to a single world. As we move deeper into the 21st century, space is becoming more accessible. Private companies are developing rockets, spacecraft, and space stations, expanding the possibilities for who can go to space and what they can do there. Governments are forming new partnerships, working together on projects that no single nation could accomplish alone. The Moon is once again a target for exploration, this time with the goal of establishing a sustainable presence. A base that could serve as a laboratory, a waypoint, a proving ground for the technologies needed for Mars. Robots continue to push farther into the solar system, visiting comets, asteroids, the outer planets, sending back data that reshapes our understanding of how planets form, how solar systems evolve, where life might arise. The silence of space holds no judgment, no opinion on whether humanity should venture beyond Earth. It simply exists, vast and patient, waiting for us to reach outward if we choose. And we have chosen, again and again, to send our machines, our messages, and ourselves into that silence, to touch the void and learn what it can teach us. The journey changes us. It gives us perspective, humility, wonder. It shows us that Earth is precious, that the thin shell of atmosphere protecting it is fragile, that the diversity of life it supports is a rare gift. It also shows us that we are capable of extraordinary things, that we can solve problems that seem insurmountable, that we can work together despite our differences, that we can dream of distant worlds and make those dreams real. Tonight, as you drift towards sleep, think of the astronauts who looked back at Earth from the moon and saw it whole for the first time. Think of the cosmonauts who lived aboard Mir, enduring isolation and hardship to expand our knowledge. Think of the rovers on Mars, still exploring, still sending back images of a world we have never walked upon but hope to visit someday. Think of the Voyager spacecraft, beyond the edge of the solar system, carrying their golden records into the darkness, messages of hope and curiosity cast into the cosmic ocean. These are not just stories of technology and achievement. They are stories of human courage, persistence, and vision. They remind us that we are explorers, that we carry within us a need to discover, to understand, to reach beyond what we know. Space travel is not about escaping Earth. It is about understanding our place in the universe, about honoring the curiosity that makes us human. It is about looking up at the night sky and asking questions, about building machines that can carry us to places we have only imagined, about believing that the future holds possibilities we cannot yet foresee. As you close your eyes, as your breathing slows and deepens, as the day's worries fade into the background, rest in the knowledge that above you, right now, the International Space Station is orbiting, a small, bright point of light if you looked up at the right time. Inside it, people from different nations are living together, working together, looking down at the same Earth you stand upon, sharing the same wonder at the beauty and mystery of existence. The stars are still there, waiting. The cosmos stretches on, infinite and patient. And we, small as we are, fragile as we are, continue to reach toward it, one small step at a time, one mission after another, one dream after another. Not because it is easy, but because it calls to something deep within us, something that has always wondered what lies beyond the horizon, beyond the sky, beyond the limits of what we have already achieved. You have done enough for today. Close your eyes, rest, and dream of other worlds. Dream of footprints on the moon, of rovers climbing Martian hills, of spacecraft carrying our messages to the stars. Dream of the future, when more people will go farther than we have gone, when the children of today will become the explorers of tomorrow. And sleep, knowing that the journey continues, that the story is not over, that every night as you rest, somewhere out there in the vast, quiet darkness, humanity is reaching toward the infinite, one gentle step at a time. Good night.